The implementation of the Stack Abstract Data Type, ADT, using an array is one of the simplest and most commonly used methods to realize the last in, first out, LIFO, structure, where the most recently inserted element is the first one to be removed. In an array-based stack, all elements are stored in contiguous memory locations, and the stack is managed using an integer variable called top, which keeps track of the index of the current topmost element. When the stack is created, the top is initialized to -1, indicating that the stack is empty and no elements have been inserted yet. The underlying array is declared with a fixed maximum capacity, which means the stack can hold only a predefined number of elements. And attempting to push elements beyond this limit causes an overflow condition. The push operation in the array implementation inserts a new element into the stack by first checking whether the stack is full. If top equals max size 1, the stack is full, and no more elements can be inserted. If not full, the top variable is incremented by 1, and the new element is stored at array top. This operation is extremely efficient because inserting an element requires only increasing an index and assigning a value, both of which take constant time O(1). The pop operation removes and returns the topmost element from the stack. Before performing a pop, the implementation checks whether the stack is empty by verifying if top equals -1. If the stack is empty, an underflow condition occurs because there is no element to remove. If not empty, the value at array top is stored temporarily as the return value, and then the top value is decremented by 1 to move the pointer to the next available element. Like push, the pop operation is also O(1), because it only involves simple arithmetic and array access. Another essential operation supported by the array-based implementation is top or peek, which returns the value at the current top position without removing it. This operation is used when algorithms need to inspect the most recent item yet preserve the stack contents. Peek requires checking for underflow before accessing array top, and if the stack is not empty, the value is returned directly. The isEmpty function simply checks whether top equals -1, while isFull checks whether top equals max size 1, helping algorithms ensure safe push and pop operations. The simplicity and speed of the array-based implementation make it ideal for many applications, especially those where maximum stack size is known beforehand and performance is critical. Since arrays provide direct indexing, accessing elements is very fast, and the stack operations do not involve the overhead of dynamic memory allocation. This makes array-based stacks particularly suitable for embedded systems, compilers, mathematical expression evaluators, and systems where memory allocation must be predictable and controlled. For example, in infix to postfix conversion and postfix evaluation, an array-based stack provides fast push and pop operations that are used repeatedly to process operators and operands. Similarly, in balancing parentheses or checking well-formed expressions, the array-based stack holds symbols and supports constant time retrieval and removal. Function call management in low-level systems also uses an array-like stack structure, called the call stack, though managed internally by the system. However, despite its advantages, the array implementation has some limitations. The major drawback is its fixed size, because the maximum capacity must be declared at creation time. If the declared size is too small, the stack may overflow during execution. If too large, memory is wasted. Unlike linked lists, arrays cannot grow dynamically unless special techniques such as dynamic array resizing or manual memory reallocation are used, which complicates the simple structure of the stack. Another drawback is that arrays require contiguous memory allocation, and in systems with fragmented memory, allocating large arrays may be difficult. Additionally, although array-based stacks are extremely fast in theory, in environments with tight memory constraints or rapidly changing workloads, the fixed size becomes a practical challenge. Nevertheless, the deterministic nature of array-based stacks, where memory allocation does not change during execution, makes them the preferred implementation for time-sensitive programs. For instance, in expression parsing and syntax checking, knowing the exact stack size helps avoid unpredictable behavior. Similarly, array-based stacks shine in applications like evaluating recursive functions without actual recursion, where temporary data is pushed and popped continuously. In such cases, predictable memory use is far more important than dynamic growth. The overall performance of array-based stack implementation is highly reliable because operations rely only on the top index and do not involve pointer manipulation, memory allocation, or garbage collection issues. As a result, using arrays allows the stack to operate in a lightweight and consistent manner, which is highly valued in algorithm design, numerical simulations, and low-level programming. Even in modern programming languages, array-based stacks remain a foundational approach for understanding how LIFO structures work, and many built-in stack libraries internally use arrays for their efficiency. In conclusion, implementing the stack ADT using arrays provides a straightforward, efficient, and fast method to support push, pop, and peak operations with constant time complexity. Although the fixed capacity is a limitation, the array-based model remains widely used because of its predictable performance, ease of implementation, and suitability for algorithms that rely on frequent stack operations. Its role in both theoretical computer science and practical software development makes it one of the most enduring and essential techniques for implementing stack data structures.